Hello everyone. In this video we are going to discuss this research paper complexity analysis of quantum teleportation via different entangled channels in the presence of noise. This research paper is published in IET Quantum Communication in 2022. These are the authors of this research paper, and in this paper authors have shown the teleportation of a single qubit quantum state via six different kind of entangled channels, and later they have shown that in the entangled channels, if the entangled channels is affected by noise, then what is the fidelity is basically the difference between two quantum state. It is a measure of difference between two quantum state. So the quantum state before the teleportation and after the teleportation, the difference between these two states, the measurement is called fidelity, and they have shown that fidelity, how the fidelity varies depending upon different entangled channels and different type of noises. So let's start. The first topic we have to understand for teleportation is entanglement. What is entanglement? So entanglement is a phenomena in quantum mechanics where two or more particles become correlated in such a way that state of one particle cannot be described independently regardless of their spatial separation. That means suppose there are two particles, so their properties are in such a way that we cannot describe the property of single particle independently. If we know the property of one particle, then we also know the property of other particle. Means they can be any distance apart in the space. So mathematically this equation psi of AB is not equal to psi of A, means ket psi AB is not equal to ket psi A, tensor product ket psi B. That means if psi A and psi B are the properties of two different particles, those are entangled. So if the psi AB is a combined state, then it cannot be written as a product of the individual quantum states. Next is the teleportation. What is teleportation? Teleportation refers to transfer of quantum information from one particle to another without direct physical interaction between them. This process is achieved using entangled particles and classical communication. So suppose let us consider there are two parties, say Alice and Bob. So Alice want to transmit a quantum state or teleport a quantum state to Bob, a quantum information to Bob. So they have to, first of all, they have to share an entangled channel between them. So when they share an entangled channel, then they will use certain quantum operations to to first entangle the quantum state, quantum message with their existing quantum and channel, the entangled channel, and then they will apply certain operations, Bell basis measurement and other control operation. And also Alice need to communicate Bob via classical communication channel, after which Bob will apply certain unitary operation and recover the teleported state. So objective of this teleportation scheme is teleport a single qubit quantum state via six different entangled channels. In this research paper, the authors have used six different entangled channels. Bell channel, it is a 2 qubit entangled channel. GHZ channel is a 3 qubit entangled channel. We will look one by one what are the channels and what is the teleportation protocol. The next is the 2 qubit cluster state, then 3 qubit cluster state, then it is Brown et al state is a 5 qubit entangled channel, and Boras et al state is a 6 qubit entangled channel. The first entangled channel is teleportation via Bell channel. So this m is the quantum state that we are going to teleport via this entangled channel. What is entangled channel? Psi is equal to 1 by root 2 cat 0 0 plus cat 1 1, and this quantum state m, we are calling it here as quantum message. uh, m cat m is equal to alpha cat 0 plus beta cat 1. This state here m will be teleported from this qubit to the last qubit. Here we are making the measurement. So this is the quantum circuit representing the teleportation protocol. Mathematically we can solve this by applying these operations. First we have to take the tensor product of these two, m and psi, and then apply this CNOT gate, then Hadamard gate, and then these two operations. We can easily see that this message m will be transmitted, will be teleported to the last qubit. This uh, this circuit inside this dash box is the entangled channel, that is the bell channel here. So this is the circuit represents the complete protocol for teleportation via bell channel. Next is the teleportation via GHZ channel. Same, the quantum message is same, but now the entangled channel is different. Psi is equal to 1 by root 2 cat 0 0 0 plus cat 1 1 1. So inside this dash box we can see the entangled channel. Here is the quantum message m, and after that we have to apply these operations, C naught operation, Hadamard, and then Hadamard on this qubit. And basically these ABCR 000 means initialized to 000, because 000 plus 111 is one of the GHZ channel. If we take these ABC as 000, initialize them to 000. If we take them 001, then this GHZ channel will change. It will be an entangled channel, but maybe different kind. Say like 001 110 and plus sign between them, and after that there may be a negative sign, 000 minus 111. There could be 8 different possibilities, a b c. All of them had two choices, either they could be 0 or 1. Depending upon the choice of ABC, we get different 8 different GHZ channel. Similarly for the previous one also, in case of bell channel, there are only two qubits A and B, and they have two choices, either 0 or 1. So there could be 4 type of bell channels. Okay, and here GHZ channel could be of 8 different types, depending upon the choice of A, B, and C. If we take A, B, C as 0 0 0, then we will get this state cat 0 0 plus cat 1 1. If we take them 1 1 1, that we will see that we will get 0 0 0 minus 1 1 1. And depending upon the other choices, we will get entangled channel, different entangled channels. Later, in the later slides, we will see that authors have also calculated quantum cost. What is quantum cost? Quantum cost is basically the number of uh, quantum operations or quantum gates that are being used in this circuit, in this teleportation. So more quantum cost means it will increase the complexity. So we will see in the later slides. So the next one is teleportation via 2 qubit cluster state. So here quantum message is same, and the 2 qubit cluster state, this is the 2 qubit entangled channel. Here this is generated like this, means this 2 qubit cluster state, the quantum circuit to generate this 2 qubit cluster state is here, 2 Hadamard gate followed by a control Z gate. So basically what we are doing is, here also A and B could have 4 choices, 0 0 0 1 1 0 1 1. So depending upon them we will get different 4 type of different entangled channels, and this message M from here to be teleported to here. So these are the operations we have to apply. Next is the teleportation via 3 qubit cluster state. So 3 qubit cluster state, similar to 2 qubit cluster state, we have Hadamard, then 2 controls at gate, and ABC. If we take ABC as 0 0 0, we will get this entangled channel. If we take different ABC, we will get a different 3 qubit entangled channels. In the For details, you can refer to this research paper. We will provide the link in the description. Go to the research paper. You will see that authors have plotted a table for different scenarios. Means they have calculated for this, means calculation is shown only for this, but they have calculated others also, and they have shown, authors have shown that how these operations will change if we take ABC as 000 or 001 100, something like that. All the 8 possibilities are given in the research paper. For more details, you can refer to the research paper. So this is how the teleportation is done through 3 qubit cluster state. Next is the teleportation via Brown et al. State. Brown et al. State is a 5 qubit entangled channel. So this is how we generate the Brown state inside this box, and after that we have to teleport this message M from here to the last qubit. So these are the operations we have to apply. This operation, particular operation, you will see in every quantum circuit. This is called Bell basis measurement, means a Hadamard and then a control node and then a Hadamard gate. It is basically used to entangle this first state with our entangled channel. Means this message that we are teleporting with our entangled channel, if we apply these two operations, it will be completely entangled with us. Then we will apply these certain operations, control node, Hadamard control node, and then swap gate and all these kind of gates, and finally we will reach from here to the last qubit. You can do very easy calculation, and this is psi. This psi represent here is the Brown et al. State. Next is the 6 qubit Boras et al. State. This message M is to be teleported through this entangled channel. Here the notations are given down below, that phi, the ket phi plus minus state is basically the Bell state. Psi plus minus is also Bell state, means as we have seen previously that 00 ket 00 plus ket 11 is a Bell channel. If we take AB as 00 and if we take AB as 11, we will get ket 00 minus ket 11, and if we take 10, then these two we will get, and we have written this Boras state in terms of these uh, Bell channels. So this is a 6 qubit entangled channel, and the quantum circuit for this channel is given here. This is teleportation via Boras et al. State. Uh, Here inside this box is the Boras et al. State. This is a 6 qubit entangled channel, and M is the message, quantum message, that we are going to teleport from this qubit to the last qubit. This is, I have already told you that this operation is used to entangle this quantum uh, bit, means qubit, with our existing entangled channel, and these are the other operations that we have to apply. Now you may wonder how the authors got these operations. So for that you have to mathematically calculate it on paper and verify that, means main objective is to get this state M is alpha cat 0 plus beta cat 1 from this qubit to the last qubit. For that, whatever operation you require, you apply those operations and you will transfer this message from here to the last qubit, and these are the operations that authors had applied. Now the next part is quantum noise. What is quantum noise? It refers to inherent uncertainty and fluctuations in the quantum system at a quantum level. These fluctuations arise due to probabilistic nature of quantum mechanics and can have a significant impact on the behavior of quantum system. So what we mean by this statement is, a quantum computer working with these entangled channels may not perform ideally because it requires ideal conditions like a very low temperature to perform very well, and all these other physical factors that are required to perform ideally. But these external factors, these environmental factors, affect the performance of a quantum computer, and it generate uncertainty, fluctuations, and these kind of this is due to probabilistic nature of quantum computer, quantum mechanics. So these these fluctuations or these uncertainties can be classified into 6 different kinds. So these 6 different kind of fluctuations or uncertainties are called quantum noise. They are bit flip noise, phase flip noise, bit phase flip noise, amplitude damping, phase damping, and depolarizing noise. So one by one we will look uh, at them and see that how can they be mathematically modeled, and then we will see that their impact on our then our teleportation on our teleportation scheme. The first one is bit flip noisy environment. So bit flip noisy environment occur when the name itself suggests that it flips the bit of the quantum system. So the qubit 0 changes to qubit 1 and vice versa. So either due to intrinsic or extrinsic factors, means to model these in mathematically or mathematics, we have these two matrices E0b and E1b. They are 1 minus under root of eta b, suffix b represent the bit flip noise, and eta b is the noise parameter. Noise parameter means if we take eta b equal to 0, so that means is completely there is no noise in the system. So if we take eta b equal to 0, here you can see that the first operation is E0b, E0b, it is 1 minus eta b times identity matrix. So if eta b is equal to 0, then it is literally under root 1 minus 0 is 1, and identity matrix will not change the quantum system, so it will remain unchanged. And here in the second, if eta b equal to 0, that means there is no noise, so this matrix will completely become 0, and E1 will have no impact on this. So therefore E0b will be becomes the identity matrix, and there will be no change in the system because the noise is 0. As the noise increases, this factor start to reduce, and this under root eta b, this will start increasing, and here you can see that it is a NOT gate, that is the X gate. So it will flip it. Basically what a X gate does is it flip 0 to 1 and 1 to 0. So as the noise keep on increasing, this E1b will have more and more impact, and when the noise will become 1, noise becomes 1 means eta b equal to 1, then this quantum, the first matrix will become 0 because 1 minus 1 is 0, and then identity matrix will vanish, and this will remain, means it will completely change the bits of the quantum system. 1 will become 0, means cat 1 will become cat 0, and cat 0 will become cat 1. Okay, next. Next is the phase flip noisy environment. As the name suggests, phase flip means is flip the phase of the quantum state. Like the bit flip noisy environment, in that the quantum bit from ket 0 changes to ket 1, but here the uh, ket 0 state changes to minus ket 1, means the phase is changed, but in the case of ket 0 it is unchanged. Means the phase flip noisy environment occur when qubits phase is changed from cat 1 to minus cat 1, and it remain unchanged if the qubit is 0. The Krauss operator for phase flip noisy environment are given by these equations. Like the previous one, E0WW we are using for a suffix for means phase flip noisy environment, uh, and 1 minus eta w I is the identity matrix, means if eta w equal to 0, that means it will become the identity matrix, and it will have no impact on the mm, quantum state. Otherwise, if here it is eta w times z, if eta w is not equal to 0, means it is greater than 0, then it will have impact, means it will change the phase of ket 1 to minus ket 1. The third type is bit phase flip noisy environment. The bit phase flip, as the name itself suggests, that it flip the bit as well as the phase of the quantum state. So the Krauss operator for the bit phase flip noisy environment are given by this equation. E naught f is equal to again 1 minus eta f times identity matrix, and eta 1 f is equal to 1 minus under root eta f times y. So this is how we represent the bit phase flip noisy environment through matrices through cross operator. The next type is amplitude damping noisy environment. The Krauss operator for amplitude damping noisy environment are given by this equation: E naught a equal to 1 0 and this matrix, and similarly E1a. So a complete description or complete calculation for these amplitude damping and other kind of noises is given in the research paper. You can refer to that. The authors have shown complete calculation and also how these matrices will act on particular qubit one by one. They have shown the complete calculation. We will provide the link in the description. You can refer to that paper. The next type is phase damping noisy environment. So in phase damping noisy environment, the Krauss operator for phase damping noisy environment are given by this: E0p, E1p, and E2p. So these are the three matrices uh, that tells us about the Krauss operator that tells about phase damping noisy environment. The last type is a depolarizing noisy environment. In depolarizing noisy environment, the Krauss operator are given by these equations. There are four different type of matrices that will act as a means we have identity matrix, then we have X, then we have Y, and then we have Z. So all these four matrices act simultaneously one by one on the quantum state, means depolarizing noise seems to have the maximum impact. We will see in the results that whether it have the maximum impact of noise on the teleportation protocol or not. So next is the fidelity. Fidelity is basically the closeness between two quantum states. This it is a measurement of closeness. Fidelity is a measure of how closely final state of the teleported system matches with the original state. So suppose we have a state psi, and after the teleportation we get psi 2. Psi 1 and psi 2 are suppose two states before and after the teleportation. So difference between psi 1 and psi 2 can be measured with the help of fidelity. So here is a mathematical formula to calculate the fidelity. F is equal to, this is bra psi rho out and cat psi. So this is basically the first is the inner product, then outer product, and then inner product of the quantum state. Then psi is the original quantum state, and rho out is the density matrix of teleported state. So means teleported state after the impact of noise, it will we can determine it only with the help of a density matrix. So the formula to calculate the fidelity is given by this expression. So here is how variation of fidelity against the noise parameter means. In case of Bell channel, the teleportation via Bell channel, this x-axis represents the noise parameter, this y-axis represents the fidelity. So as the noise parameter is 0, the fidelity is 1, means the teleported state is completely matches with the original state. As the noise parameter start increasing, the fidelity start getting dropped, and in some of the cases, like you can see that this pink one is a depolarizing noise, the fidelity keep on decreasing, and it reaches to its minimum when eta is equal to 1, means the noise parameter becomes maximum, the fidelity becomes the minimum in the case of depolarizing noise. And in other channels it increases after a certain value, around 0.5, because means due to the symmetry in the entangled channel, like in GHZ channel 000 plus 111. If you flip these uh, these qubits, it becomes 111 plus 000, so that it becomes again the same. So that's why the fidelity again increases and reaches to its maximum value. So in GHZ channel also show the similar trend. The depolarizing noise has the maximum impact, and other increases and decreases according to means according to different entangled channels and different noise. Similarly, in case of 2 qubit cluster channel, in 2 qubit cluster channel, the phase damping has the maximum impact, and these other graph can be read that depolarizing noise after that, and all these others. And in 3 qubit channel also, depolarizing noise have the maximum impact. The fidelity is minimum for 3 qubit entangled channel in case of depolarizing noise. Similarly, in Brown et al. State and in Boras et al. State, we can see that graphical representation of fidelity against the noise parameter. So these are the simulations or outcomes after the means how they have plotted these kind of graph after calculating the fidelity. Fidelity is calculated between the initial quantum state and the teleported quantum state, the density matrix of teleported quantum state, with the help of noise. For this more description, refer to the research article. The link is provided in the description. Now in the beginning I talk about a quantum cost. What is quantum cost? Quantum cost is the number of primitive reversible gate used in designing circuit. Means suppose a single qubit gate like Hadamard, the NOT gate, control NOT gate is also taken. They all have quantum cost equal to 1. And suppose we have a swap gate somewhere. This swap gate can be decomposed into 3 control NOT gates. So swap gate will have a quantum cost equal to 3. Similarly, control Z gate, we can write them as Hadamard, C naught Hadamard. So it will also have a quantum cost equal to 3. So therefore the quantum cost of each reversible gate can be calculated by counting the number of related basic gates. So in the previous slides I have talk about, means suppose we have a bell channel 00 plus cat 00 plus cat 11, 1 by root 2 cat 00 plus cat 11. So in that case, if we change A and B, we will get a different entangled channel, bell channel. We will get 4 different type of bell channels. So the quantum cost for each bell channel is given in the research paper. You can refer to that. And the average of these quantum cost is given here. This 11 represent that in the case of bell channel, the 4 bell channel, the quantum cost, average quantum cost is 11. Second one is the GHZ channel. 15 means in all 8 kind of GHZ channel, the quantum cost, average quantum cost is 15. The 2 qubit cluster channel, there could be 4 possible, so average of 4 is 15. Then 3 qubit cluster channel, the quantum cost average is 21. The Brown et al. Channel, the quantum cost is 24, and in Boras et al. Channel, the quantum cost is 38. So this is the maximum quantum cost that we have. Means it is obvious that more using more number of qubits increases the quantum cost of the teleportation protocol. So this is all the study done in this research paper. For for more details, please refer to the research paper. Link is provided in the description. So thank you so much. Thank you from my side. Have a great day.